We were discussing the different components of surface and interfacial tension, and now we have reached a stage where we know that when we are considering the interaction. So, fundamentally when we are considering the interaction between two dissimilar molecules or similar molecules, the interaction we are considering is based on van der Waals interaction as well as polar interaction, and that gets manifested in terms of surface and interfacial tension, which also has components of van der Waals interaction as well as polar interaction. So, we first talked about the how to mathematically obtain an expression for the magnitude of the van der Waals interaction between two molecules of two dissimilar materials, provided the interaction, the self interaction of the molecules V11 and V22 are known, and we came up with a formula that V12 LW is given as under root of V11 LW and V22 LW. Then we looked into certain cases, and we realized a very interesting thing, that only by considering van der Waals interaction, that is when we talk about considering different terms, it is fine. When by considering van der Waals interaction, you in fact cannot explain colloidal stability. We have seen that, because two surfaces, or I just physically put this as a statement in a different way, two similar apolar colloidal objects in a apolar liquid medium, we have seen that they will always come in contact. So, colloidal stability cannot be explained. So, we now realize that in order to have colloidal stability, even a stable colloid, it is important to have additional interactions, and the second interaction that we told that we will consider will be the polar interaction. We started to define the again terms that can mathematically represent the polar interaction, and we have defined two terms, essentially the electron donor or the proton acceptor parameter gamma minus, and the conjugate parameter, that is electron acceptor or the proton donor term, and these terms are for every component. It is not the interfacial terms, it is for individual components. Or in other words, they are the constituents of the polar component of surface tension of a material I. So, these are the individual constituents of the polar component of surface tension of a material I, and how they are related is based on some sort of a geometric mean multiplied by 2. Further, we note that for polar interactions, delta G 1 to AB, that is the polar component of delta G between two dissimilar surfaces, so only the polar component is given by this particular relation, where it is essentially addition of the two cross interactions, which is obvious, because we already argued that in order to have polar interaction you need to have opposite polarity, and if you have opposite polarity in the neighboring molecules, let us say this is 1 and this is 2, of course, the plus component of this is going to interact with the minus component of this, leading to attraction, and similarly the minus component of this is going to attract the or interact with the plus component of 2, and that is exactly what you see, because this delta G 1 2 also corresponds to when they come in contact, and it is some sort of an additive addition of the two cross interactions. So, based on these understanding, we continue our discussion on the polar component of surface and interfacial tension. So, what you see now on your screen, we have already discussed all those things. So, this is what we just discussed, and we can also rewrite G 1 2 considering the same old picture. This is very similar to what we had written in the earlier case as delta G 1 to LW as gamma 1 to LW minus gamma 1 plus gamma 2. Here I would like to make a statement and want to sort of initiate some bit of thought in your mind. While considering the van der Waals interaction, delta G12 is equal to delta G12 LW. My question is, can we write that while considering the polar interaction, that we consider only a system where we have polar interaction, and the answer is a big emphatic no. Why? Because I have been telling this to you for a while, and I think now all of you understand, and based on this particular discussion for next 2 minutes you will understand it in an even better way, that you can have situations where the interaction is only van der Waals. But if you have a system which is polar, where there is polar interaction, please do not forget that LW interaction is always present. So, this statement is not correct, but you can individually look into the term delta G12 AB, that gives you sort of the free energy change due to adhesion of two surfaces which have polarity. What is the contribution of the polar components of surface and interfacial tensions? Therefore, what you can combine this one, and what you get is this particular formula. Please do not try to remember or mug it up, you can very easily derive it. It looks a little cumbersome, but it is very simple. What you get? This is the polar component of interfacial tension. I will just write, in order to compare the expression of the van der Waals component of interfacial tension, because ultimately your gamma 12 is going to be gamma 12 LW plus gamma 12 AB. And here you note something interesting. We have already seen that this term is going to be positive no matter what is the magnitude of gamma 1 and gamma 2 LWs. However, here you see that gamma 12 AB can be positive or negative, and it depends on the numerical values of these individual components, because these all come under root. So, individually all these terms are positive, and since all these terms are positive, now one in fact needs to look, or in other words, gamma 12 AB is going to be positive if the total cohesive polar interaction, because this is interfacial tension of 1, this is interfacial tension of 2. So, this is polar interaction, but between the gamma plus and gamma minus of the similar objects. This is within 1, this is within 2, and this is the adhesive interaction, that is the polar interaction between dissimilar objects. So, if the cohesive interaction, the strength of cohesive interaction exceeds the strength of adhesive interaction is combination of these two terms, cohesive interaction is combination of these two terms. You can also identify that in the transparency. And as I promised, this will be made available to you. So, this is the cohesive terms and this is the adhesive terms, and depending on the strength. So, if the strength of the cohesive terms is higher than the strength of the adhesive terms, then you also have gamma 1 AB as positive. But if the strength of the adhesive term is stronger or higher than this, then gamma 12 AB can be negative. right. You can have a situation theoretically that gamma 1 2 AB is negative, but again gamma 1 2 is positive, and that will depend on the relative magnitudes of the polar and van der Waals component of interfacial tension. Why a negative value of gamma 1 2 LW is going to be important for us is simply we relook into the problem of two colloidal particles of same material 1 trying to come in contact within a liquid medium 3, because the change in the free energy, or we can write it as gamma delta G 131, which is two objects of 1 coming initially, they are dispersed in liquid 3 and then they are coming in contact, and you can find it out, the expression, you can do it yourself, the expression turns out to be minus 2 gamma 1 3. So, now if we consider a system where we have both polar and van der Waals interaction, this 1 3 LW is going to have two terms, and here we actually have expression for both the terms. Just 1 2 we just replaced it with 1 3, which is fine, it is more of a pedagogic difference. And here you can see that this term is always going to be positive, and this term, depending on the relative magnitudes of the 4 constituent terms. What are the 4 constituent terms? Gamma 1 plus, gamma 1 minus, gamma 3 plus, gamma 3 minus, they can be positive or negative. Now, if both are positive, no point, the colloid is again unstable, because both the terms are positive, this is positive, delta G 131 is negative, because and therefore their adhesion is guaranteed. So, that is not an exciting situation. So, the only way can be obtained is gamma 1 3 as a whole has to be negative, because if it is negative only then delta G 131 will become positive, and therefore, what would it mean that the two surfaces, the two colloids of 1 will thermodynamically be no longer favored to come in contact. So, the only condition for colloidal stability is gamma 1 3 has to be negative, which would imply that delta G 131 becomes positive. And now we relook, considering all the concepts we have built slowly, how this can be negative. So, necessary condition for this to be negative is, of course, gamma 1 3 AB has to be negative, and now you also understand under what condition this is possible. This is possible when the adhesive polar interaction, the adhesive part of the polar interaction the adhesive component of the polar interaction exceeds the cohesive component of polar interaction. So, that only this condition will make gamma 1 3 AB negative, but there is a additional condition. This can be negative, but if its numerical value is lower than the magnitude of gamma 1 3 LW, I repeat, this is negative. Let us consider a situation is negative. However, gamma 1 3 AB, the numerical value is lower than gamma 1 3 LW. What would that lead to? That will lead to this to be positive. So, this because this is anyway positive. So, this again leads to colloidal agglomeration. But there is a difference. So, what is important in this particular case is the colloids will agglomerate, but you have competition. So, the van der Waals force is responsible for their van der Waals component of interfacial energy is responsible for their agglomeration, but the polar component is trying to oppose that. But numerically the strength of van der Waals force is stronger and therefore they agglomerate. So, the only condition under which you can obtain a stable colloid is you need to have negative interfacial value of gamma 1,3 arising out of the polar interaction, and numerically this has to exceed the value of gamma 1,3 LW, which will always prefer adhesion of the colloidal particles in air as well as in a liquid medium. So, that is sort of what we wanted to discuss about the individual components of surface tension. There are certain additional interesting observations that one can make. One of them is, if you look at the expression for gamma I AB, and what did we consider? We considered that it is sort of a geometric mean of gamma I plus and gamma I minus. Sorry, I am just missing out, it has a prefactor 2, that is not very important. One of the consequences that we in fact discussed was if either gamma I plus or gamma I minus is equal to 0, either is very important, then gamma I AB is equal to 0. So, this is very interesting. So, you tend to apparently feel that when you talk about the surface tension or you calculate the surface tension of this material, there is no effect of the polar component, which is correct. There are lots of surfaces or materials which either have and which actually sort of obeys this condition. There are many surfaces where, for example, gamma plus is non-zero, but gamma minus is 0, or the opposite is also true, and these are in fact called monopolar surfaces. So, if I straight away ask you that you have, let us say, colloids of some monopolar material. So, do they always adhere? So, are these type of colloids always unstable? So, is the question clear? We are seeing that if one of the components is 0, then there is no effect of the polar component of surface energy for a specific material, and in this case we are asking, or I am asking, like what we had observed for purely apolar substances, this is what we got. This is always negative, this term is always negative, and therefore colloids are never stable. So, for monopolar colloids, is it the same situation? Well, please do not jump on to conclusion, because when we are considering a colloidal dispersion even with a monopolar colloid, this gamma 1,3 term in fact contains gamma 1,3 LW and gamma 1,3 AB, and there is no need to discuss gamma 1,3 LW any further, it is always positive. But please be careful, this gamma 1,3 AB in fact contains these terms. And that is very interesting. Let's assume that gamma 1 plus is 0. Okay. So, what it means that indeed this term is 0, and that also means that gamma 1 minus is non-zero. This term is 0, this term is also 0. However, this term is non-zero. So, the situation of if you have a monopolar colloid is dispersed in a polar medium, is not similar to an apolar colloid in apolar liquid. Why? Because indeed you do not have any contribution coming in terms of the total surface energy of this material 1 due to the polar interaction, but due to the cross interaction, the adhesive interaction in a polar liquid, this term will be non-zero. And depending again on the magnitudes, this term in principle, at least mathematically or theoretically, has the possibility that this term numerically exceeds this term, and therefore gamma 1,3 can become negative. And the moment gamma 1,3 becomes negative, delta G 131 would become positive, and that would lead to a stable colloid. So, this is possible. One can further twist the question. What happens? You have a monopolar colloid in a monopolar liquid, and again do not jump into the conclusion, please try to find out what are the terms that are present. Well, if it turns out that gamma 1 plus is 0 and gamma 3 plus is also 0, then of course all the terms are non-zero. So, there is actually no contribution of gamma 1,3 AB, it will tend to 0. Why? It is very obvious. Look at the expression, gamma 1 plus makes this term and this term 0, gamma 3 plus makes this term and this term 0. However, continuing with the discussion of the same case, monopolar colloid in monopolar liquid, if you have a situation that for the colloid, let us say gamma 1 plus is 0 and for the liquid, let us say gamma 3 minus is 0, or it can be vice versa also, then again in this expression, I will quickly write down the expression again for your understanding. This is the term corresponding to gamma 1,3 AB, and you will again find that well this term does not contribute, this term does not contribute. However, there can be one term, there is one term which is non-zero. So, again in principle this term contributes. So, gamma 1,3 AB will indeed have a negative value, and depending on its relative magnitude of gamma 1,3 AB with gamma 1,3 LW, again you can theoretically at least get a positive value of delta G 131. So, even under this condition, it may be possible to get stable colloid. So, we now have had a pretty nice picture of this so called colloidal stability. We looked into several conditions. One condition that sort of unconditionally leads to unstable colloid is if you have an apolar colloid in an apolar liquid, it has to be unstable. It will definitely, the particles will definitely agglomerate. On the other hand, if you have a polar liquid and a polar colloid, there are possibilities, and you have to look into the individual numbers. So, there will be polar interaction, and you have to look into the relative strength of the adhesive and the cohesive interaction, and you may achieve stability. And you can also have a monopolar colloid and a polar liquid, or a monopolar colloid and a monopolar liquid medium, and under appropriate condition, even in those cases it is possible to have some sort of stability coming out. One question I will leave for you is that if you have apolar liquid, apolar colloid in a polar liquid, how that is going to contribute, right? So, if you have apolar colloid, what it means is that gamma 1 plus is 0, gamma 1 minus is 0, and that in fact you can see for yourself that the cohesive terms, the adhesive terms which can lead to a negative value, they actually do not work out. So, it is gone. So, if one of the components is apolar, the cohesive interaction goes to, the adhesive interaction goes to 0. Apolar means that gamma 1 plus gamma 1 minus both are going to be 0, or gamma 3 plus gamma 3 minus both are going to be 0, and therefore, in principle theoretically you cannot explain colloidal stability. So, with that I will stop, and there are certain additional aspects associated with this when the colloids are coming in contact. I will discuss that and move on to one very fascinating thing, that is the surfactant molecules, in the next lecture. Thank you.